joined today by Christian. Everyone say hi in chat to Christian. Christian, do you want to say hello? Do you want to say anything about yourself? Christian, I forgot to unmute you. Would you mind saying hello again? Sorry.
Hello, I'm Christian, second year Maths and Stats student at Mansfield College.
Fantastic. Brilliant stuff. Right, okay. Sorry, we practiced and everything, and then I forgot to unmute you. It's really rude of me. Okay, Christian's joined us today to do some problems. Coming up today, we've got problems involving pigeons with Christian. In fact, we've got an entire pigeon-themed live stream for you today because Christian's showing you some problems involving pigeons, and then I've got a problem involving pigeons as well. So after a break in the middle, we'll do more pigeon problems. You're welcome to join us in chat. Can't hear James. That's a new one. James is really quiet. Let's try and fix that. It's going to happen sooner or later, right? I know where it is. Testing 1 2 1 2. Testing loud and clear 1 2 1 2. That might be better. Give it 20 seconds and we'll see. Oh, 1 2 1 2. Jessica can't hear me. Leah can't hear me. Pico Cozy says can't hear me. Molly says hello. Better or worse? Let's do a little better or worse. Let's try and get that working. Much better says Funky Pigeon in chat. Welcome Funky Pigeon. Thank you for coming along and thanks for being a pigeon. Much better. Right. Sorry. RIP anybody who was using RIP anybody headphones. And now many people are saying can't hear you and much better. Louder. We've got a mix of opinions due to stream lag. Okay, I've had both sorts of stream problem coming in and out. That's great fun. Right, okay, this is great fun. Some people think it's working. I'm going to plow on and we'll see what happens. Okay, cool, right, good. You're good, much better. Even Carly Ray Jepson says that we're doing much better now, which is great. Dish, you can hear me. Okay, I'm going to run the intro one more time. Pretend nothing's happened. We're going live. Coming up today, we've got problems involving pigeons with Christian. And in fact, it's a pigeon-themed live stream because then we've got problems with pigeons with me and problems with my audio throughout. But let's get started with the Pigeonhole Principle, which I need to switch over to here. Cool. Okay, I've got some pigeons on the board and some pigeonholes to put the pigeons in and something called the Pigeonhole Principle. Christian, do you want to take it away and explain what the Pigeonhole Principle is?
So the Pigeonhole Principle basically says that if you have M pigeons and N pigeonholes, where M is greater than N, then there's at least one hole which has to have at least 2 pigeons in.
Okay. Let's break that down. Okay. So here I've got M pigeons. I've got M is 5 pigeons. And I've got N pigeonholes, these boxes that pigeons live in. And I've got 4 of them. And M is bigger than N. Okay, let's write this down over here. If M is bigger than N, then what did you say happens?
And at least one hole has at least 2 pigeons in, with the emphasis on the at least parts.
Aha! Okay. At least 2. I've run out of space for the word pigeons. There we go. I'll just put it here. There we go. Okay. I put these pigeons up so that we could experiment with actually trying this out. I'm going to try and fit the pigeons into the pigeonholes to see what happens. I guess the Pigeonhole Principle kind of feels quite basic. It feels like a kind of obvious statement, right? Like you've got more pigeons than pigeonholes. So yeah, of course, you're going to have to put two of the pigeons in the same pigeonhole. There's no way to put all of the pigeons in different pigeonholes. But it's surprisingly subtle in what it actually says. Here's one attempt at putting the pigeons in pigeonholes. And I've put 2 here and I put 1 in each of the other pigeonholes. Does it have to be like that?
No.
So I guess I think I want to explore like what else can happen. So I guess the thing to remember is that we could have all of the pigeons in the same pigeonhole, if they wanted to. We could cram all of the pigeons in the same pigeonhole. And then the fact that Christian said is still true. At least one of the pigeonholes has at least 2 pigeons in. In fact, it happens to be 5 pigeons in here. And I think there's some other sort of interesting cases as well. Like, we could have something like this, where there's more than one pigeonhole with at least 2 pigeons in it. It's actually sort of surprisingly difficult to get this statement at the bottom here to be precise and correct, so that you're not overstating it. The pigeons sort of don't have to be fairly distributed across the pigeonholes. The reason I'm saying this is because we're going to try and apply this principle to some problems, and when you're doing the problems with kind of abstract pigeons and pigeonholes, it's quite easy to get confused about what has to happen. It's worth remembering the pigeons could all be in the same pigeonhole, or there could be more than one counterexample pigeonhole. Somebody in chat says, very cool pigeon drawings, which is very polite of them. Last week Lauren had a really cute picture of a frog, and I tried to make the pigeons cute, but I couldn't work out how to make the pictures of the pigeons cute. Okay, that's one version of the pigeonhole principle. Do you want to tell them the other version of the pigeonhole principle we were going to talk about?
So the other version is if you have n equals... Wait, let me just get it right.
So there's another version with more pigeons. I'm going to copy and paste some pigeons around a bit.
So the other version says if you have n pigeons where m equals kn plus 1 and n pigeonholes, then at least one hole has at least k plus 1 pigeons in it.
Okay, so there's a refinement. If m is kn plus 1, if m equals kn plus 1, so this is a kind of improvement. If m is equal to kn plus 1, then at least one hole has at least how many in it? At least k?
K plus 1.
K plus 1, okay. Do you want to explain why that's true?
So this is true because if you try distributing just kn pigeons very evenly across all holes, so I think we've got
9 pigeons, I think.
Okay, yeah.
Maybe. Some of them are kind of on top of each other.
So if we try distributing 8 of these pigeons into the 4 holes, the most even way we can do it is with 2 in each hole.
I'm doing it. I mean, everyone knows what 2 pigeons in each square looks like, but somehow I've started putting them in the pigeonholes, so I've got to completeness. There we go, okay.
So when we come to the final pigeon, one of the holes has to have k plus 1 pigeons in, because k is 2 in this case.
So I suppose it's like, even at maximum capacity, if you've got k pigeons in each of the holes already, then the last pigeon that you try and put in, the kn plus 1th pigeon that you try and put in, it takes that over to k plus 1. But I guess it's important, even in this kind of more complicated statement, I guess it's important to say again that even though in the argument that Christian's just presented, in the argument we spread them out evenly, the pigeons again might not be spread out evenly when it actually comes to the pigeons being in the pigeonholes. I guess we're imagining pigeonholes that can take any number of pigeons, so they might not be spread out like they were in Christian's argument. There could be one pigeonhole with absolutely loads of pigeons in, or multiple pigeonholes with quite a lot of pigeons in. Okay, somebody in chat has just asked about are there any practical applications of the pigeonhole principle? We're about to do some applications. Are any of them practical? What do you think?
Not really.
I hate it when somebody says they've lost all sound is the worst. I feel like we should have someone just monitoring whether my sound is turned on or not. Cool, right, good. I've got this control panel for sound that's not very good. Right, okay, we're going to do some problems. Ooh, do we need to rephrase this when kn plus 1 is even? Could kn plus 1 be even?
Yeah, if k and n are both odd, but there'll be an odd number of pigeonholes with at least one of the pigeonholes will have at least k plus 1 pigeons in still, because there'll be an odd number of holes instead.
Sure, okay, yeah. And somebody in chat's got a suggestion. Why isn't it m greater or equal to k n plus 1? And actually, that's still true. So we could edit our statement further to be like m bigger than or equal to k n plus 1. If you've got more pigeons, you get more problems. And just having k n plus 1 was enough to force this problem of having k plus 1. Okay. Somebody's highlighted the even question. I think we decided we don't need to rephrase it when kn plus 1 is even. I think it's still true. Should we do a quick demo? If I take away one of the pigeonholes. Sorry, pigeon. So now I've got... I'm going to take away some of the pigeons as well. If I've got 7 pigeons and 3 pigeonholes...
then that means our k is 2.
Yep. I've got k is 2... And it still works because even if I put 2 pigeons in each pigeonhole, then I've got this last leftover one that has to be a 3rd pigeon in one of the pigeonholes. So even if in this example k is 2, n is 3, and m is greater than or equal to 7, in fact in this example m is 7, then there must be at least one hole with at least 3 pigeons in. Okay, cool. Good stuff. Right. Okay, we've got some problems that use this, and they are pretty abstract, but they're also pretty interesting. So we're gonna go and do them. Christian, what's your first application of Pigeonhole Principle?
I actually can't remember.
We had a running order planned. Oh, I think something about the Bodleian Library.
The first application is whether 2 books in the Bodleian Library have the same number of words.
Ooh, okay. I'll try and write that up. There are 2 books in the Bodleian Library. Do we need to give context here that the Bodleian... Oh, goodness, I should definitely have learned how to spell Bodleian before... Oh, goodness, I should definitely have learned how to spell library before going live. Embarrassing. Bodleian Library with the same number of words. I guess 2 different books, not just 2 copies of the same book.
Yeah.
So context here is that the Bodleian Library is a massive library in the middle of Oxford. It's kind of like our central library. I have spelt it wrong. There'll be people in chat telling me that I've spelt it wrong. I need to put an A in here. Do you want to carry this for a moment while I try and fix the spelling?
So the Bodleian Library is a library around Oxford. There's a few different places where it's at. And it's one of the largest libraries in the UK. It has 12 million books, I believe, from my quick Google just before the live stream.
Okay, so there's this massive library. And I suppose it would be quite a hard search to go and look through. The people in chat are correcting my spelling now. I fixed it. It'd be like quite a hard task to go through, look at each of those books, count how many words were in that book, and to make a list maybe, and then go and search through for 2 books that had exactly the same number of words in. You seem quite confident. Why are you confident that there are 2 books that have the same number of words?
Well, the Pigeonhole Principle.
Ah, right, okay, yeah, so it's back to the...
So, to do this, we need one other fact. And that fact is that the longest book of novel in the world has about 11 million words.
Okay, I can see where you're going with this now. So the longest book in the world has 11 million words.
Something like that.
Something like
characters that.
Okay, maybe this is true. Okay, so let's be formal. How do you actually, if you were gonna sort of write out your proof with the Pigeonhole Principle, how would this actually work? What are the pigeons?
So I would assume that no 2 books are the same length of words.
Okay. So assume no 2 books Oh, I can't even spell two. No two books have same number of words. Okay. Now I suppose...
So because...
No, go, sorry.
So because no two books have the same number of words, that means that they all have to have a different length. So we might have one that has 0 words, one that has 1 word, 2 words, so up to 11 million.
Yeah, I suppose this is sort of a maximal set. Up to about 11 million words. Okay.
And that is at most 11 million and 1 books.
Sure. So that's only 11 million and 1 books.
So by the time we come to selecting the 11 millionth and second book, it has to have the same length as one of the books that we've already looked at.
Brill. Yes. Okay. So problem. This is I saw someone in chat say proof by contradiction. It's this kind of style of proof where Christian assumes that something would work, and then found some sort of contradiction in there. That means that the original assumption is false. Okay. So there must be two books to have the same number of words. Okay. I guess phrased in terms of pigeons, if you're like me and you like rephrasing everything, this is a bit like giving each book to a pigeon. And then each length of a book, so each length is a pigeonhole. So each possible length of book is a pigeonhole. And then the pigeons have got to get into the pigeonholes, but there are m bigger than n, pigeons, more pigeons than pigeonholes, so there must be two pigeonholes, the same number of pigeons. Cool, right. People in the chat are posting their own favourite examples of the Pigeonhole Principle, which is exciting, given that we've got a running order. Let's see if any of the ones on our running order come up in chat. Somebody's mentioned birthday problem, which is interesting. I guess you could apply to the birthday problem to say, if you've got 400 people in the room, then you've definitely got two with the same birthday. Happy birthday to the pigeons. And somebody else said that it was like the case with square roots of numbers that we talked about a couple of weeks ago, which is true. Cool. I like the way that this proof is sort of non-constructive. This doesn't tell me which two books in the body and have the same number of words. It doesn't give me any idea what they are or how long they are. This kind of like non-constructive proof is pretty interesting. You don't see a lot of it in school, but you do see some of it at university. Kind of proof that things exist without actually saying where they are. So
we just have to find where they are next.
Yeah. So if we actually want to find them, we probably do have to go and look at all the books. I love that part of your proof, by the way, I really love, is that you considered the book with no words, which is such a sort of mathematician construct that you can throw it into the argument. It's fine. You can count it. The book with no words, though. Publish. It's like John Cage 433. Right, okay. I've got a problem next. My problem involves a square, as a lot of my problems do. So my problem is, here's a square. It's got side length 1. I would like you to prove... oh no, hang on. I need to say what I'm doing first. Okay. Given 10 points inside this square, I would like to prove that 2 of them are a distance square root 2 over 3 apart or less. Okay, does that make sense? So if I want to find 10 points inside here, and where I say wherever you put 10 points inside here, wherever you put 10 points inside here, I'll be able to find 2 of them that are a distance that are kind of close together, root 2 over 3 apart or less. Okay. People in chat have got suggestions. Book with no words is the only book I'd read. A wordless book is a book that tells a story just through illustrations. Oh yeah, like a picture book. Okay, those exist. I'm going to give chat a minute to think about this problem because I've just written it on the board in very messy handwriting. And I'm going to try and catch up with chat. Oh yeah, sorry, I didn't explain what John Cage 433. That was a reference to a music. Lucy's seen this while doing interview prep. But we didn't actually ask it in an interview as far as I know. I'm going to scroll back at chat. Pick two of the same books? Yeah, I guess if there are two of the same books, then it's easy.
Yeah.
I guess what Christian said was even if all the books are different, then there's still two of the same number of words. Grant Sanderson was here and is now off. People disagreeing about how many words there are. Yeah, okay. Stanley's got it. This comment looks like it's going to be in French, and then is actually the name of a book with lots of characters. Oh, lots of characters. Okay.
Yeah, I've probably got the facts mixed up.
Doesn't really matter, does it? Cool. Yeah, Smith squares. Okay, right. Okay. Cool. Okay. Can you put more than 1 point in the corner? Yeah, you can if you like. If you put more than 1 point in the corner, over here, so if you put your 10 points up here, then I will pick two of those points and say those are really close together. Those are a distance root 2 or 3 apart or less. This or less is doing a lot of work in the statement. Okay. So it's kind of key when you see these problems to identify what's going to be the pigeons and what's going to be the pigeonholes. Yeah, and there's somebody's linked to John Cage 433 with the comment absolute banger, which is amazing. Aaron's got a kind of optimal placement argument, which is interesting because you've got to think about different cases if you start arguing about what the kind of optimal placing is. It's kind of interesting to imagine optimal placing being what happens if the points kind of repel each other, maybe. It's not obvious to me what the optimal placing is. 1 over 10 is 0.1. So they've each got a possible area of 0.1 that it can be in. Min distance is 0 apart, that's true, because they could all be in the same part. And the maximum distance, okay. So Leah's got this argument about dividing up all of the space into kind of circles involving root 11 or something. I think working out how to tessellate those spaces together into the square is a little bit tricky. Sort of loci question. Okay. Each square requires at least the area of a circle, so the circles are allowed to overlap. So if you're doing an argument, if your argument works as saying, well, each point needs a kind of circle around it that's its space. Well, those circles are allowed to overlap so long as the points aren't too close together. If your argument works like that, you need to be a little bit careful. They're allowed to share that space. They're not allowed to be close together. Safe in chat wants to cut the square into 10 parts, and I saw Molly down 9 is the square number just less than 10. Something about 9, something about 10. And I think I saw Zach a while ago splitting the square into 9 parts. Christian, have you seen this problem before? Do you want
to? Yeah, I sort of. I've heard of it, but I haven't given it a proper go before.
Do you want to have a go at solving it live?
So I think that the suggestion of 9 in the comments was a good suggestion because it is a square number, so we can split the square into small squares, and it does leave 1 left over afterwards.
Yeah, 9 plus 1 is 10.
I've got to test how well I can draw on this now.
Oh yeah, okay. You're in this. Off you go. Yes, look at this. You can have 9, but 10 would be a distance less than square root over 2. Square root 2 over 3.
That's worked good.
Brilliant, yeah. It's going well.
So I need to get my points. I'm going to do a different colour. So we can distribute 9 of the points into each one of these squares randomly.
Good do.
But none of these, we don't know anything about these points. They could be as far away from each other as possible, or they could be right next to each other on an edge. So this doesn't give us too much information. but we have a 10th point we've still got to put in. And that means at least one of these squares has to have at least 2 points. So I'm going to put another one in this square here.
Just as an example, this square over here might have oh, there you go, might have 2 points in. I think you're now done because the side length of the square is 1, so the side length of each of these boxes is 1/3. So the furthest apart that these 2 points could be is if they're in the corners.
2 opposite corners.
Yeah. If they're in the corners, then their distance is √2/3. Quick bit of geometry, I suppose. That's √2/3. So I guess here the pigeons are the points, and the pigeonholes are these ninths of the square that Christian split it into. So if you split it into 9 squares, then because 10 is bigger than 9, one of the squares, we don't know which, has to have at least 2 points in it. If it's got 2 points in, then the furthest apart they could be is at the corners of the square, the distance √2/3. Do we stream on Twitch? No, because of the adverts. And K-pop fam ages ago, asked how big's the square? It's side length 1. Cool, right, good, okay. This is a practical application of the Pigeonhole Principle. I kind of didn't say at the time because I didn't want to spoil this question. This is a kind of bound on social distancing. Sorry, I've been trying not to mention the pandemic in this live stream so far, but this says that if this is a room and you've got 10 people in there, then we know that 2 of them must be a distance √2/3 apart. So this is kind of a logical extreme of looking at distance between things. Right, okay. I love this question. I'm biased. I put this one in the live stream. Right. What's next? Oh, this is we've got a more abstract one. This was social distancing, but maybe we don't want to think about that too much. Right, okay. Shall I write up the next one?
Yeah, you can.
Sure, okay. We're trying to do a variety of problems. If you don't like one, there'll be another one along in a couple of minutes. Okay. So here's a new one. I'm going to give chat a moment to do this one as well. Chat was doing pretty well at the last one. Let's say you're given 5, let's be really careful, positive whole numbers. Prove that there are 3 of them that add up to a multiple of 3. I'm going to do an example. Christian, can you give me 5 numbers that are positive and whole numbers?
7, 14, 2, 5, and 28.
Wow, okay. So I think I can pick... so Christian's given me five numbers. If I pick this one, and this one, then the sum is 21. And 21 is a multiple of 3. And my claim is that I can always do this. And whatever 5 numbers get picked, then I can find 3 of them that add up to a multiple of 3. Pretty sure this was a UKMT Olympiad question. Possibly. Can the numbers be the same number? Yes, the numbers can be the same number. If Christian had said 7, 7, 7, 7, 7, then I can pick 3 of the 7s, and so my sum is 21. Again, multiple of 3. People in chat, have you got suggestions of numbers or suggestions of this? Why am I saying, is there a difference between saying positive whole number and positive integer? No, I'm just not sure if everybody's happy with the word integer. They don't actually need to be positive, but for this to work, but yeah. Brill. Okay, cool. Maybe it's chaos, but I still want to give chat the chance to suggest numbers. Yeah. So are they random or consecutive? They could be anything. They could be random numbers. They could be your favourite numbers. They could be last week's lottery numbers. They could be any 5 numbers. And Nigel is leaving us to watch the chase. Fine. A, B, C, D, E. Yeah, must total 3n. So people are bringing algebra in here. I saw other people bringing in modular arithmetic, which we've mentioned before on the live stream. So I want to talk about this in terms of pigeons, if that's okay. So I'd like it if someone in chat or someone on live stream could bring pigeons into this. Oh, Raphael's giving me 5 numbers. Brilliant. Oh yeah, look, a bit of stream delay. 77665 is good. I can pick 765, and I'll get 18. Lucy, 24, 30, 5, 6, 50 is in chat. People are using larger numbers now, so this is getting stressful. I can pick 24, 36 and get a multiple of 3. 1, 2, 4, 5, 7. I wonder if people in chat are trying to prove me wrong. 1, 2, 4, 5, 7. I can pick, oh goodness, 5, 7. Am I stuck? No, I'm not stuck. 1, 4, and 7. Gives me 12, which is a multiple of 3. This is fun. Pigeonhole, yeah. Ooh. Yeah, there's a sort of probability argument in chat that I'm not totally happy with. Everything should have pigeons brought into it, says A in chat. What if they're all prime? What if they're all prime? I mean, if they're all 3, then great. I can pick 3, 3, 3, and I'll add up to multiple of 3. X, Y, Z, X, Y, X, Z, 5, 3. Algebra. 1, 4, 7. Yeah. Zach's with me. Okay. There are 9 possible choices. Okay, Molly says there are 9 possible choices of 3 numbers. Is that true? There's an interesting question about how many different combinations of numbers there are. I suppose people are thinking of those as the pigeons, and then we're going to argue that there we go. We just have at least 3 even or at least 3 odd. Okay, so I guess Grant's thinking you have at least 3 even or at least 3 odd, because 5 is bigger than 4, so there must be 3. There must be 3 that are even or 3 that are odd. But that doesn't really help me with multiples of 3. Think about the digits 1 to 9. Yeah, okay. Yeah, parametricity has given me some massive numbers. But I think Graham's numbers are multiple of 3, 0 is a multiple of 3, and I think 196883 might be multiple of 3, so I choose those 3. 5 choose 3 is 10. 8 possibilities of numbers. Okay. At least 2 pairs of numbers which have the same residue modulo 3. Okay, so people are starting to think about...
might help.
Yeah. Do you want to take that idea and run with it?
Yes. So there's 5 numbers, and there's 3 different possibilities for what its residue modulo 3 is. Either 0, 1, or 2. Okay. And I'm going to try and find a good place to write.
Yeah. If I go down a bit under these numbers, I think we've got the hang of what this is. But not showing this next square. There's a bit of space.
So there's 3 possibilities, either 0 modulo 3, 1 mod 3, 2 mod 3. And the Pigeonhole Principle says that at least one of these 3 pigeonholes will have at least 2 numbers in. But so there might be 2 numbers in 0 mod 3, 2 in 1 mod 3, and 1 in 2 mod 3. But that doesn't quite solve it. So we're going to try and eliminate one of these, one possibility, and that's if there's at least 1 number in each group. So if there's at least 1 number in each group, we're going to pick 1 0 mod 3, 1 mod 3, and 1 number that's 2 mod 3. And if we sum these together, that sums up to 3 mod 3, which is 0 3.
I'm just going to interrupt really quickly to help out Nicki Minaj. Nicki Minaj in chat says, what does mod mean? Mod here just means it's short for more than a multiple of. I suppose you could think of it like that. So before, when we were talking about how numbers were either a multiple of 3, I guess everything is either a multiple of 3, 1 more than a multiple of 3, or 2 more than a multiple of 3. That's how multiples of 3 work. So these are the 3 different sort of pigeonholes that Christian's considering, whether things are 0, 1, or 2, more than a multiple of 3. Cool. That's all. Yeah, so they could have... Okay, and I've interrupted Christian with the point of having, if you've got one in each pigeonhole, then you can add those together, and you get a multiple of 3 if you do that.
So we're going to assume that there isn't one of each type of number. So that leaves us with only 2 holes. So let's cross out one of these. So we're eliminating one of these groups, because we know that if we have all 3 groups filled, then we can find 3 numbers which satisfy this. So we're now left with 2 pigeonholes. I'm going to use the other definition of pigeonhole principle, that if you have kn plus 1 pigeons and n pigeonholes, then one of the holes has k plus 1 pigeons. So we have, let me change my colour. So we have 5 pigeons, basically, and 2 holes. This means that one of the holes has to have at least one of the holes has to have at least 3 pigeons in.
Yeah.
And actually, that's quite strict. You can't have 2 having 3 in. Because
you've only got 5. You've only got 5 numbers or pigeons here. So yeah, at least one pigeonhole. In fact, one pigeonhole has 3 numbers in. So wrapping it up, you've got 3 numbers that are the same remainder when you divide by 3. And I'll add those together. Because if I've got 3 in here, if I had 3 in here, then I'd have 3 that were all multiples of 3. That's great. I'll just add them together. That happened over here, 24, 36. If I've got 3 that are multiples of 3, great news. Similarly, if I've got 3 that are each 2 more than a multiple of 3, then when I add them up, bit of algebra to check, when I add them up, I'll get to 6 more than a multiple of 3. But hang on, 6 more than a multiple of 3 is a multiple of 3. Because 6...
And then someone says, why did I get rid of 1 mod 3? So that was just me generalising to having 2 groups. So I got rid of one randomly. But if you had 1 mod 3 and 2 mod 3, one of them would still have 3 in, and 3 lots of 1 mod 3 is a multiple of 3 again.
So I suppose there's kind of 2 steps to this argument. I'll just write it up. Step 1 is, what if the pigeons are using all 3 pigeonholes, i.e. there's a pigeon in each pigeonhole, at least 1 pigeon in each pigeonhole. And then there's kind of step 2 to say, okay, step 2, what if the pigeons, terrible handwriting, sorry, are only using 2 pigeonholes? So in the first case, if there's pigeons in all of the pigeonholes, then Christian's plan is to add those 3 numbers up, 1 from each pigeonhole. A 0, I think that's multiple of 3, I think that's 1 more, and I think that's 2 more. If on the other hand the pigeons aren't using all the pigeonholes, for example if they're not using the 1 mod 3 pigeonhole, then the plan is to pick the pigeonhole that's got 3 pigeons in and use those 3 numbers. Okay, so this is pretty confusing, because there's kind of 2 separate cases. It's a kind of double pigeonhole principle argument. And again, this argument is kind of non-constructive. This doesn't actually tell me which 3 numbers to use. It can kind of tell me where to look if I start working out what the remainders are when I divide by 3. Yeah, so people in chat are quite worried about the odd and even mod 2 argument. I guess I was worried that having 3 even numbers. So I saw this argument in chat, and I didn't talk about it too much. I'm going to talk about it just very quickly. There was an argument in chat to say we've got 3 even numbers. or 3 odd numbers. The problem is when you add 3 even numbers together, you don't always get a multiple of 3. For example,
2, 4, and 8.
2 plus 4 plus 8 is 14, which is not a multiple of 3. So somehow it's true that in each case we either have 3 even numbers or 3 odd numbers, but unfortunately adding up 3 different even numbers doesn't always give you what you want, which is a multiple of 3. Cool, right, okay. This was a tough one. Should maybe have done this last, but in fact we have one more. Should we do one more? What do you think? Yeah, let's do one more to finish with. Might as well, we got a square again. So, last one. Christian set this one for me, and I couldn't do it for weeks. So, it's last, I guess. This is our last Pigeonhole Principle problem. Do you want to state what the question is?
So the question is, if you have a square with side length 2 and 9 points, do there exist 3 points which form a triangle with area less than or equal to a half?
3 points which form a triangle. I remember this now. Form a triangle with area. Say it again. Sorry, area.
Less than or equal to a half.
Okay. So we're given 9 points, which is quite a lot. And we're asked, do there exist 3 of them that make a kind of small triangle? So sort of a little bit like they're putting the points a big distance apart in the previous one, root 2 over 3. Here, can you put all the points kind of, is there a way to put them far enough apart so that there isn't a triangle of size 1/2? Or do they always collapse together? Or is there always an example of 3 of the points that are close enough together? Cool. And I guess someone said, are there three odd numbers that don't add up to a multiple of 3? That's a great question. 1 plus 1 plus 3 is 5. Yes. I put 3 as the last one because I was trying to make it that way around. K-pop fan, yes. Cool. Sort of wondering if we should set this one as homework or something. What do you think? Do you think we should show them the answer to this, or let them think about it?
We could do.
Or the geometry arguments are pretty nice. Yeah, I think I'm going to be mean. I think I'm going to leave this as a sort of homework puzzle that we'll come back to on a future live stream. I hope that makes sense. Someone says, are the notes available afterwards? Yes, this YouTube video is going to be up after we're live as well, if we are live now. Cool, right, okay. I think we're going to stop the Pigeonhole Principle stuff there with a homework problem. Thank you very much, Christian, for coming on the live stream.
Thank you.
Good stuff. I'm going to put an ad break up and try and catch up with chat. Are you hanging around for the rest, or do you need to run off?
I'm going to run off. I might hop onto the chat for a while.
Yeah, okay. There's your ad break. Okay, brilliant.
I'll hop off now. Thank you.
I will see you around. Nice to have you on as ever. Let me turn the cameras back to this one. There we go. Cool. Right. Okay. Brill. Quick ad break while I do some admin to. Yep. Let's move these pigeons out. They're not needed for this. Huh? You can have one pigeon there. Ad break. Cool. Right. Okay. Good stuff. Quick ad break. I've got the standard ad break. People in chat are trying to answer the question from the homework problem. Okay, brilliant stuff. After the break, we've got another problem involving a pigeon, and I want to advertise a random event in Oxford to you. Not random, maths event. Yeah, thanks, Christian. Cool. So here's the ad break. It's 1729 plus 999 plus 1001. I'm hoping that takes you a little while. Okay. Is there anything important I've missed in chat? People are telling me, ooh, split the square up. Yes. No homework, show answer. Split the square up. People are telling me how to do this sum, which is good. Okay. Yes, so splitting the square up like we did before is a really good idea. And without spoiling the problem for everyone, I'm going to say that is a good approach. Right, cool. Today, the live stream is sponsored by Group Theory again. group theory gives us a nice relation. If you have a group, then when you see a sum like this, you have a choice. You can do the first two things plus the third thing, or you could do the second and the third things added together, and add that to the left thing. So here you could do 1729 plus 999, which is tough, and then add 1001. Or by the power of group theory, you could do this sum first, 999 plus 1001. Aha, that's 2000. To get this. This rule is called associativity. Oh, why do I do this to myself? Oh no, I'm not even gonna try. Right, okay. This rule is called associativity. And it's one of the things that groups do. Watch out for this in other operations. So addition does this. You have this choice. You can add together the first two, or you can add together those two. And not every operation does this. So multiplication does this. A times B times C is the same thing as A times B times C. But if this was to the power of A to the power of B to the power of C is not associative, because A to the power of B then to the power of C is not the same thing as A to the power of B to the power of C. Those are different. Cool, right, okay. And somebody's done it in base 16 as well. Great, okay. Ad break, still not a funny joke, but we're going to keep trying it out. I've got a different puzzle for you. It still involves a pigeon. I'm going to bring this pigeon with me. Where have I put this one? We down here somewhere? Ah, yeah, okay, here's the puzzle. So the puzzle works like this. There's a pigeon, and it starts at this house. This is like a map looking straight down at where the pigeon is. It's an enormous kind of Godzilla-sized pigeon. And it wants to get from this house to this house over here. I should give you some distances. So the distance is 3 miles or kilometers or whatever in that direction, and 2 miles or kilometers or whatever in that direction. So, you know, as the pigeon flies, the best way to do that is to fly from the first house to the second house, like that, in a kind of straight line. Okay, my problem is slightly different though. My problem is that the pigeon would like to go via this river. No expense spared on the graphics today. We've got a nice river in there. I've got a PhD in fluid dynamics. I know what rivers look like. Blue rectangles. Okay, so the idea is the pigeon, it would like to go via the river, so it wants to fly to some point on this perfectly straight river, and then fly to the other house. Okay, I should tell you how far away the river is. The river is an entirely realistic and to scale distance of 1. He says consulting notes. So that's 1, that's 2, that's 3. Look, it's not to scale. So the pigeon's going to start at this house, it's going to fly to somewhere on the river, and then fly to that house. And the question is, what's the shortest route? Let's go quickest. What's the quickest route? Okay, I hope that makes sense. So the pigeon's going to start here. Let's put some more helpful direct distances on. So this is 1. This is 2 plus 1, so this is 3. And the distance between the houses is 3. Okay, hope that makes sense. This is 1, 3, and the 3 across. Right, cool. Okay, good stuff. And we're going to solve this. I'm going to show you how to solve this in 3 different ways. Oh, one of them's in chat. People are quick today. Oh, birds don't fly in straight lines, says someone in chat. Oh, my pigeon is very clever, and there aren't any roads for it to follow. So it's going to fly as the pigeon flies, which is like how the crow flies, but better. So it's going to fly in. My one's going to fly in straight lines because it's going to be quick. It knows where it is. Cool, good, right, okay. Oh, is this like brachistochrome? My word, okay. People have seen some minimization problems before in chat. Brilliant stuff. I'm going to do this in 3 different ways. Kind of to show you how I would solve this problem. Then there's a nice trick for this problem. which at first looks like a kind of random trick, and then I want to explain the trick and say what the trick means. Okay. Oh, this reflection idea is in chat. Have people seen this before? People have seen this problem before, right? Or you're just really quick. This is a great idea. Okay, reflection method is going to be number 2. Yeah, someone else has put mirror it as well. Yeah, okay. Wow. Okay, great. So the kind of first method of doing this problem is to just write it down. Just write down the problem as some kind of minimization. You know, I want the quickest, shortest route. So I'm going to write down a load of algebra. So my method 1 is going to be algebra. Chat is way ahead of me on method 2, clever trick. Oh, do you try and make an equilateral triangle? Ah, okay, maybe. Maybe we could try and think about nice angles that this could do. My first method though is just pretty unexciting. To put in some distances, call this x. Call this, I suppose this is 3 minus x over here, and then this distance, do some Pythagoras stuff. Oh yeah. So this is 1 plus x, root 1 plus x squared over here, and then this distance is going to be root 9 plus 3 minus x squared. Good stuff. Okay, that's my distance. I want to minimize this. If you're in year 13, then you maybe know enough calculus to go and minimize this. If not, then let's minimize it using Desmos. So I've got this kind of Pythagoras thing of what I want to minimize. Oh, this is my first method. So if I go to Desmos, I type in square root of 1 plus x squared plus square root of, oh no, hello, leave that one, plus square root of 9. This is where I find out everyone in chat is better at Desmos than me. Yeah, this is a typing disaster. I want a squared here. There we go. I get this function for what the distance is, and this has got some minimum in here at, according to Desmos, looks like it might be at 3/4, 5. Okay, so either by using calculus or by using Desmos, looks like the minimum for this is that x is 3/4 when the distance is 5. Okay, and if you know enough year 13 stuff, then you know how to differentiate this. And you can go and do a fun sort of calculus problem to differentiate this, solve the equation to find the minimum. I'm not going to make you do that though. Right, proof by Desmos. Good stuff. Okay, which is sort of somewhere over on the left. There's a second method, which is a kind of trick. And I'm all for clever tricks. I don't mind a clever trick, especially if it makes things easier than doing proof by Desmos or proof by algebra. And lots of people have already put it in the chat, more than I can name call now, but several people have said an idea, which is to reflect on the problem. No, reflect this house up above the perfectly straight river, and to draw in a line from where the pigeon is going to go to this house up here. Now, what the pigeon wants is it's going to fly to the river, and then from the river, fly to the house. Its mirror image, as it does this bit, its mirror image is going to fly up here. This line is the same length as this line because it's a reflection. So all we need to do is make sure that this pigeon's journey here and then up to this house is as short as possible. And the way we do that is kind of semi-obviously by making this a straight line. So we want, let's see if I can move this point. Come on, Miro, come on. Oh, no, it's not going to let me do it. No, I've got too many objects on my whiteboard to snazzily move that. One more go. No. To move this, to make this a straight line. If we make this a straight line, whoop, like that. If we make this a straight line, then everything's really nice. We kind of get a bunch of similar triangles. There are some equal angles going on. Everything's super nice. I'm going to try and draw that on better than that, actually, because I want to make a point about this. Okay, so I hope this makes sense. That there's this idea that if you reflect up here, then what we really want is we want these two things, these two bits of the journey together to make a straight line. Okay, cool. Right. I'm going to try and redo this to show where that is. Ah, come on, I just want to move the little circle. No. Let me move the circle. No. Okay, right, cool, that'll do. Okay, so we end up with something like this, where I suppose in this kind of perfect configuration, where you have this straight line, and once you put the straight line in, it's kind of clear. The geometry gets much easier once you put the straight line in. And more importantly, you get this kind of fact that this angle alpha, well, it's going to end up matching this angle over here, this angle alpha over here. So our method two is reflection trick. To say reflect up here, that shows that you've got equal angles, then you do similar triangles, brilliant stuff. So it comes up here, similar triangles, yada yada, work out what the angles are. You don't have to do any calculus, so that's a bonus. Of course, this thing with the equal angles in is something that you might have seen before if you're doing A-level physics. If you're doing A-level physics, then this idea of equal angles should be familiar to you. So my method 3 is physics. This should be familiar to you as just how reflections work. So as well as the method of reflecting the house in the river like it's a mirror, you could think about this as a laser-guided pigeon, which we all study in physics A-level. Laser-guided pigeons. If you've got a laser shining from this house and the river is a mirror, then the laser will bounce off the mirror and you can sort of line it up so that it hits the other house. And then you tell the pigeon to fly along that laser line. So that's one way of doing it. I suppose said differently, if you know about lasers, you know that lasers travel in straight lines and they take the shortest distance between 2 points. Actually, that way of thinking about physics turns out to be a really good way of thinking about physics. There are other versions of this problem like this that you can do with calculus. At university you learn more calculus for doing problems a bit like this. But the kind of central idea behind a lot of different bits of physics. So there are things like reflection, laws of reflection with equal angles. There are laws like refraction. There's something called Snell's law, which has exactly one fan in chat. So there's Snell's law, and there's also facts that you learn at university, like gravity bends light rays. All of these kind of different physics facts are kind of best understood as light takes the shortest route. In time, said one way, or in terms of minimising action. So kind of, I really like ways that mathematics can come up with new ways of thinking about problems. I think there's at least 3 ways to think about the pigeon flying between 2 houses problem. Especially when this relationship between equal angles and laws of reflection turns out to be secretly a kind of deeper bit of physics that lots of really advanced physics is thought of in terms of this idea of minimising things. Okay, actually in all of these cases there's a harder problem that people often do. So once you've seen the reflection in a mirror trick, there's a harder problem to do with running across a beach and swimming through some water that you can do to kind of derive Snell's law in terms of this minimisation principle. I'm going to put that up on the website afterwards. Quick word about how we're doing the website. At the moment, I need to switch back to this. How do I switch back to this? It's going to be fine. Slides on this F5. Brilliant stuff. Everyone loves it. Main port switch. There we go. Quick thing about the how we're doing notes. There's some further reading. We're scrapping the email newsletter. We're no longer sending emails out. We're just going to put the further reading on the website. I'm doing that because I get better maths formatting. It was a pain trying to get all the maths into the email in a format that would display in emails. So I'm going to start putting all of it just on the website. In fact, if you've missed any of the further reading from previous emails, then instead of missing out, those are now also on the website. So if you want to read more about this sort of stuff after the Maths Club, then more links on the website. Quick plug, because I forgot to mention it, for a Somerville Year 12 study day. I'll put this on screen. If you're at a UK state school or college, then there's an event. It's called Equations and Symmetries. It's a maths talk in a couple of weeks' time. You can sign up to see a free maths talk. So that's for people in Year 12. There's a link on the screen. I'll put the link on the website as well. Cool, right, okay. Otherwise, that is the end of today's live stream, and I will see you again in 167 hours from now. Have a nice week. I'm going to hang out in chat for a little bit afterwards, answer some questions. I can see people having a go at other questions, telling me about physics, which is brilliant, and I'm going to jump into chat and talk over there. Otherwise, see you next week. Bye.